Good afternoon, everyone. Thank you for coming to this week's edition of the Brazilian Algebraic Geometry Seminar. I ask everyone to turn off their microphones so that we do not have any background noise. And it's a great pleasure to have Ugo Bruzzo speaking this week. He's currently at SISSA and also visiting the Universidade Federal da Paraíba. And he'll talk about the McKay correspondence in 3 dimensions. Ugo, please.
Thank you. Good afternoon to everybody. I would like to thank the coordinators of the seminar for proposing me to give this talk. And I'm very happy to be in Brazil, at least virtually. As I was saying before starting, I was supposed to be in Brazil personally, but I had a flight March 13. They canceled my flight, and apparently I lost the last opportunity. So I'm stuck in Trieste. And okay, so concerning my talk, it is partly a review of standard facts about the McKay correspondence in 3 dimensions, and partly an exercise. So I really am not going to tell you many original results, at least many original results done by me and my collaborators, just a little bit. And also let me start by saying that this is different. I mean, to prepare this talk, I took pieces from different papers and the work I've been doing with many collaborators. So we wrote these 2 papers, more or less written mostly in physical language and or pseudo-physical language. And also I'm collaborating, I mean, these Graffeo and Peragin are 2 students of mine, and they are doing something related to this stuff. So, the mathematical problem is the following, or at least part of the problem is the following. We have a finite subgroup of SL3C, which we call G. And then we take the quotient, C3 mod G, say the fine quotient. And then we want to find possibly crepant resolutions of singularities of this quotient. And we want to describe the geometry. And the gist of the McKay correspondence is that the geometry of this desingularization is fully encoded in the group G, in particular in the representations of this group G. Also, very much as in the case of the standard McKay correspondence in 2 dimensions, there's also a, let's say, differential geometric description of the same construction, which here, this is actually Kähler quotient construction, and I called it a Cronheimer-like construction. And it turns out that this is more suited than the GIT construction or description to deal with physical applications. And the differential geometric description turns out to be much closer to what is the application to physics of this stuff. And actually, there's been work a few years ago about this desingularization. They turn out to be modular spaces of some objects that are called G constellations. And they are obtained by GIT. So there's a stability parameter around. And then you want, which is correspond to the level sets in the Kähler quotient construction. And then one wants to understand the chamber structure for this stability parameter, what happens on the walls, etc. And what I will do is to review some facts about this 3-dimensional McKay correspondence. There's a basic paper which is due to Ito and Reid, and more papers, especially in connection with the relation with the Kähler quotient construction. There are unpublished papers by a guy, Italian, I think, who wrote a thesis in Oxford. His name is Sardo Infirri. And more recent works by Craw-Ishi and other people. And I will use an example, which is C3 modulo in action of the cyclic group Z4 as an example. It's an example which is doable in detail. It's not entirely trivial, and it helps to understand what's going on, and it helps as a warm-up to tackle more difficult problems. Part of this project, I mean, these crepant resolutions turn out to be so-called locally Calabi-Yau's. So they have, of course, they are non-compact, but they have a trivial canonical bundle, of course. And so they might carry Ricci flat metrics. And so part of the program is to find these Ricci flat metrics on these resolutions. And this is a very tricky problem. It's a complicated problem. So a key notion in this theory is the notion of age. So if G is our group, so every element in the group is some finite order R, and let's call, we are representing G into a SL3C. By the way, the choice of SL3C is also because in that way, the singularities that you get are Gorenstein. So if lambda 1, 2, 3 are the eigenvalues of G regarded as a matrix in SL3C, then you can write, and you can write these as exponents of a primitive root of the unity of order R, and you have some exponents AI, and you arrange, you call age, the normalized sum of these exponents, okay? And normalize with respect to the order of the element. So this is the age of the element. Actually, it is, actually the age depends on the conjugacy class of G, of course. And in 3 dimensions, as we are working now, the age may be 0, 1, and 2. So age 0 only corresponds to the identity. And then the classes whose age is 1 are called junior, and the classes that whose age is 2 are called senior. So up to the trivial class, we have junior and senior classes. And I will write gamma I for the set of conjugacy classes of age I, okay? And we want to apply this, of course, to the desingularization. So in particular, these are minimal models. And therefore, I will use this definition of minimal model of X. So this is a projective morphism, which is crepant. And the variety Y that we have on top is a Q factorial and has terminal singularities. So here in the notes, if somebody wants to read, I've written the meaning of Q factorial. So every Weil divisor is a multiple, which is Cartier, and the notion of singularities, terminal singularities, right? So the so-called discrepancies, so the coefficients of the irreducible components of the exceptional divisor, these AI are positive. Okay, so this is a minimal model. And in particular, in our case, where X is this affine quotient C3 mod G, for G a finite subgroup of a Z3C, a minimal model exists, and one can prove that it is a Q cohomology. Q cohomology manifolds, what is written again in this note, so some cohomological condition, but the issue here is that on a Q cohomology manifold, you have Poincaré duality. It's a condition for a sufficient condition to have a Poincaré duality. And of course, since our variety is not compact, we have duality between usual, so to say, standard cohomology and cohomology with compact supports. Okay, so we do have Poincaré duality. And then this is the theorem which was proved by Ito and Reid, which indeed establishes, as I was saying, a close relation between, in particular, the age of the irreducible conjugacy classes of elements of the group and the structure of the exceptional divisors of the resolution of singularities. So why is the resolution of singularity of X? And then what happens is that, for instance, there's a one-to-one correspondence between the set of senior classes and the basis, the compact exceptional prime divisors, so the reducible, compact irreducible components of the exceptional locus. A basis, these generate, in our situation, these generate the second cohomology of Y with compact support. So this is another set which is in one-to-one correspondence, a basis for this cohomology group. And of course, by Poincaré duality, a basis for H4 of Y. And the same happens, I mean, we have another one-to-one correspondence between the set of junior classes, all exceptional prime divisors, so compact or not, a basis for the full second cohomology group, and of course, a dual basis of H4 with the compact supports. Okay, so we have these two, I mean, we have one-to-one correspondences between these two sets of objects. Okay, and we shall see this at work in the example I've chosen to illustrate the general theory and some feature of this construction. Okay, so this is the idea. Senior or junior classes are in correspondence with the compact or all exceptional irreducible components of the exceptional locus of the resolution. And for instance, our example with Z4 is the following. So we are considering the action of Z4 on C3, which is induced by this transformation. Okay, this is an action of Z4. Of course, this group is abelian, so elements correspond to conjugacy classes. And we have 4 of them, of course, because we have 4 elements. And so we have the identity, whose H vector is 0. And then we have the element G0. And if you compute the eigenvalues and the order, of course, the order is 4, you get 1, 4 to 1, 1, 2. And so this is junior. The age is 1. And then we have a compact component of the exceptional divisor. And no, sorry. No, we have a component of which is because the junior classes label all of them. Indeed, we also have the square of G0, which is of order 2, and the age is, I mean, the age vector is this 1, 1 half, 1, 1, 0. This is again junior, right? The sum is 1. And this is going to be a non-compact component. Why we know that the first is compact and the second not compact? This is because G0 is dual to the only senior class. We have this class corresponding to G0 cube, whose age is 2, so it's a senior, and so it must correspond to a compact component. And it is dual to G0. It's the inverse, right, of G0. And therefore, this is exactly the compact component which corresponds to the first junior class. So, of course, we have no idea of the geometry of this resolution in concrete. We didn't build it, but we already know that we have one compact and one non-compact divisor. And therefore, in particular, as we saw, this also tells us the structure of the cohomology of this resolution singularity. Okay, so we have these cohomologies very easily. Okay, and for well, what is that in the abelian case? You can always study this using toric geometry. I mean, you can study the resolution of singularities, in particular, using toric geometry. And this is also technically used in the paper by Ito-Reid, who first proved the abelian case, even the cyclic case. They established the theorem for the cyclic case using toric geometry, and then they have an algebraic technique to reduce the general case to the cyclic case. It's a very complicated paper, not easy to read at all, but anyway, in the nutshell, this is what they do. First, they study the cyclic case using toric geometry, and then they move to the general case by a reduction process. So I will do this very humbly in the case of our concrete example. So, so we have the variety C3 mod Z4, and basically what you do by using a minimal set of rational invariants of the action of Z4. So rational, I mean, you pick up 3 independent rational functions of X, Y, Z, which generate the invariant ring. And there is a technique in toric geometry to construct the fan which represents the variety. You do the computations and making some choices which are completely material. For instance, you get these 3 vectors. Okay, V1, V2, V3. And then basically this is a affine toric variety, corresponds to just one cone of maximal dimension. This cone is indeed the cone generated by the 3 vectors. This cone is sigma. And then what you do is that you take the dual cone. So this cone sigma lives in a let tensored by the real numbers. Let's say that the lattice is capital N, and then M, this M here is the dual lattice. And inside the dual lattice, you have the dual cone, which basically is the cone whose points all have a non-negative action on the elements of sigma. This is the definition of the dual cone. And you take only the rational points of the dual cone, the points which lies on the dual lattice. And this is a semigroup S sigma associated to the cone. You take the algebra generated by this semigroup, you take the spectrum, and what you get is the toric variety, the affine toric variety X, which in our case is exactly C3 mod Z4. Toric geometry also offers a way to represent explicitly this as an affine variety, as a locus in some affine space. And this is done by the following procedure. So this is a kind of a review of some standard facts in toric geometry. First, you look for a minimal set of generators of the semigroup, which includes the rational generators of the rays of a sigma dual. So the rays are, okay, the edges, one-dimensional edges of this cone. This cone in our case is 3-dimensional, and it has 3 rays. And then you look for a minimal set of generators of the semigroup, which includes the rational generators of the rays. This is called a Hilbert basis. It's not a basis because the elements are not independent over Z, okay, because you have relations. what it's called the Hilbert basis. In our case, so you have to do some computations, and we developed a small package with Mathematica to compute the Hilbert base. There exist many more around, but on the market, but they are very complicated. So we made a very small, simple package in Mathematica. And in our case, you find the generators. They are 9. Since to any generator we associate a variable in a defined space, this means that in this way, our variety embeds into C9. And therefore, clearly there are 6 relations which relate these generators, and they define an ideal clearly, right? This is what is called a toric ideal, namely is generated by binomials, It's not the ideal which it's very well known. This is not the ideal which cuts X in C9. It's not the ideal of X as an affine variety in C9, because what you have to do is a saturation process. So what happens is that this ideal, the affine variety associated to this idea is reducible with components of different dimensions, and our variety is just one of these components. So you have to go and pick it up. You need a way to pick up just the component you are interested in. And this is obtained, this is a standard issue in toric geometry. It is obtained by a process which is called saturation of 2 ideals. It's the usual definition. So if you have 2 ideals, the saturation of I with respect to J is defined in this way. Okay, is the ideal of elements in A such that Fnj is in I for n big enough. And then general theory says that from the idea, you have to take the ideal which we obtain using a Hilbert basis of the semigroup, and you have to saturate with respect to the ideal generated by the product of all variables. Okay, and you get a new idea. This is the ideal which picks up the component which corresponds to our affine variety, which is a C3 mod Z4 in this case. And this idea is generated by 20 quadratic binomials. Okay, so expressed in this way, this variety is very far from being a complete intersection. Okay, it is a codimension 6, and it is determined by 20 equations. Actually, the same construction can be obtained constructing the usual affine GIT quotient. And this is interesting because it gives also a handle to another representation of the variety, which is important when you go looking for actually Ricci-Fleck metrics. So the usual affine GIT quotient, of course, is simply you take the invariant subring of the coordinate ring of C3 and take the spectrum. And so you get the same description in the sense that when you look for the ideal, I mean, this invariant subring has 9 generators. They happen to be, although here they play a different role, the invariant generators happen to be exactly these 9 monomials. You see, they are actually, they come with a weight. They come with a weight. X and Y have a weight 1. I mean, when you construct, they are simply monomials. When you look at this as the invariant subring, but they don't have all the same degree. The fact is that this is somehow related to the weighted projective space P112, and therefore the variables Z, Y, X, Y, Z come with a weight, the weight of X and Y is 1, the weight of Z is 2, so everything is of weight 4 here. And this is indeed the basis of this invariant subring. So again, we have a variety in C9, and when you look for the relations, so you look for the ideal cutting the variety, you get exactly the same 20 polynomials, 20 quadrics, as we obtained using toric geometry. Actually, this construction shows that what you can describe X as the fine cone over the image of a generalized Veronese embedding. Generalized because this embedding starts from a projective, weighted projective space. It's an embedding of P112 into P8, which is given by the line bundle O4. O4, this is not, I mean, is locally free, is a line bundle of P112. So its classes in the Picard group. If you describe the space of global sections of this line bundle, you get exactly the same generators of the invariant ring. This, by the way, this line bundle is minus is the dual of the canonical bundle of P112, and we shall. This, I believe, is related to what we are going to discover using some toric geometry again. So this X is the affine cone over some of a Veronese embedding from P112, and we shall meet P112 again. Okay. Let me check the time. Oof. So, okay, for instance, so you can construct the full resolution using toric geometry, and then we know the reason why the variety is singular is that the cone is not basic. I mean, the three rational generators of the cone are not a basis of Z3. This is the reason, from the viewpoint of toric geometry, of the fact that the variety is singular. And then what you have to do is to cut the cone into subcones that are basic. Namely, each cone has three generators, rational generators, and the three generators are a basis of Z3. Okay, and then the variety, which is no longer affine, of course, because we have in particular, in this case, a fan formed by four cones, will be smooth. And since actually we hope there's a crepant resolution, there's a way of finding the new rays. No? So what we have to do here is to add some rays and use them to cut the original cone into subcones. And then what you do is the following. This is this drawing here on the lower right. The blue dots are the points in the lattice. And then we have the black arrows that are the generators of the cone. And then you take the triangle with these vertices, the triangle whose vertices are the tips of the generators of the rays. You look for the rational points on the triangle, the points that lie on the lattice. There are two. And these graphs on the left are what I like to call the planar graphs. So the first is the planar graph of the original fan. So we just have one cone. And then here we have the two additional points or rays that we added, W2, W3. And already here we see that we have first the new rays correspond to the components of the exceptional divisor. So we shall have two components. And actually the fact that W3 is in the interior of the triangle means that the correspondent component of the exceptional divisor is compact. And the fact that W2 is on one edge means that the corresponding component is non-compact. So you read everything just by looking at the planar graph. And then you can compute, again, using toric geometry, you can really compute the two components, and you find that the compact component is a copy of the second Hilbert surface, and the non-compact component is P1 times C. And also, if you look at the new fan, there's a way to understand that the variety that you get is the total space of the canonical bundle of the second Hilbert surface. Because you start from the fan of the second Hilbert surface, you know what the canonical bundle of a second Hilbert surface is, and then there's a way to compute the fan corresponding to the total space of it, and you get exactly the same fan or an equivalent fan. Particular with these choices, you get exactly the same fan. Okay, so now we have a handle on the structure, the full structure of this resolution singularities. If you regard these resolution singularities as the total space of a canonical bundle, the compact divisor is just the zero section of it. Okay, it's a copy of F2, which is the zero section of this line band. And of course, what you can do is you can add just one ray if you want, and what you get is a partial desingularization. So it's something which dominates the quotient C3 mod Z4, but it is only less singular, but it's not smooth. In this way, what you get, again, by the same analysis, you only have one compact component of the exceptional divisor, and this is the total space of the canonical bundle of weighted projective space P112. This is related to the fact that the blow up of the singularity of the projective space is the second Hilbert surface. So, of course, Y3 is not a minimal model, in particular is not the singularization. This is related with a fact which is contained in an old paper by Grauert, which shows that if you have on a variety, you have a vector bundle actually whose dual is ample, then the zero section of the original vector bundle is an exceptional locus. It can be contracted. And indeed, this is what happens in our case. The dual of K is actually ample. So you can do this and you get exactly the blowdown. But you apply this idea, you get exactly the blowdown. Just a side remark. And now I would like to, now that we have understand completely, I would say, the situation with an example of the three-dimensional McKay correspondence, let's go on in the general theory. And let me show you this notion that was introduced, as far as I know, by Craw-Ishi, namely the notion of G constellation. So we shall call R the regular representation of our group. So it's the representation of G on the vector space generated by G itself over the complex numbers. So simply the elements of G are regarded as the basis of the space, and you act on them with the G itself. And first, this is standard notation, a G sheaf on C3 is a coherent sheaf together with the G action, which covers the action of G on the space C3. Okay, so we have an equivariant G sheaf. We call it a G constellation if it's a space of a global section is isomorph, which of course is a representation of G, is isomorphic to, as a representation, to the regular representation, is the regular representation. Okay, so a G constellation is G sheaf whose global sections are the regular representation. And you say that two G constellations are isomorphic if they are isomorphic as G sheaves. Okay, so we have this notion of a G constellation. And we have a notion of stability for G constellations. And the space of stability conditions is the space of homomorphisms of the representation ring of the group G with the values in Q. And we normalize them. We normalize them with the condition that they are zero on the regular representation. And then we say that the G constellation is theta stable. So the G constellation is F. This is theta stable whenever, for every proper non-trivial G equivalent coherent subsheaf E, theta of the global sections of E is positive, right? The global sections are a representation. So the global section of F are the regular representation. The global section of E, which is not a constellation, it's just a G subsheaf of F, anyway, is a representation, and you ask the theta on this representation is positive. Okay, so this is the notion of stability condition that we have for a G constellation, and semi-stability, of course, we also allow for equality. And this is also, this definition is also the notion of genericity that you have, for instance, for quiver representations. You say that the stability parameter theta is generic if for that value of the parameter, stability and semi-stability are equivalent. Okay, such a representation, a stability parameter, sorry, is called generic. And then you can construct a modular space of G constellations using GIT quotient. And then what you do, as usual, you start from an affine space. So this is the space of triples of G invariant triples of endomorphisms of the regular representation. And inside this vector space, you cut an affine locus N by taking the triples that commute in this sense. So, I mean, this is of course very much, this looks like some ADHM construction, no? It's the usual stuff that people know from ADHM parameterization of sheaves, from quiver representation theory, it's very similar. So you consider this N, and on this N, you have an action of the G invariant general linear group of R, which splits, of course, according to the reducible representations of the group. So you can write it as a product of the general linear groups of the say of the irreducible representations, like this. And since also actually there is an invariance under an homotety, as it happens in this kind of problems, you actually take the projective general linear group, always G invariant. And then what you do is you take the set of stable points according to our definition after choosing a stability parameter, and you take the GIT quotient with respect to this group. So you get some space, and actually you can interpret this as a fine modular as a modular space of G constellations which turns out to be fine, because you have, of course, from this, since the space is this one, and we have this skew symmetric condition, you have a map from the dual of the symmetric algebra of C3 to the endomorphisms. Yeah? You get it from here. And this gives a map from this space to this. Why this gives a constellation? This is explained a little better in the next slide. Because a G constellation, we can identify C3 with the spectrum, of course, of the symmetric, the dual of the symmetric algebra of C3, which is just a space of polynomials in 3 variables, right? So for this reason, the G constellation is a G equivariant module structure on R. And therefore, for this reason, just by taking, if you want, no, this is wrong. I should have written something different here. This is tautological. So F is the localization of R, of the module R, okay, with this representation that you get from this module structure on R. So this is stupid. Of course, this is true on an affine scheme. Here, H0 C3F is R, okay, with this structure. And so we have this space. In particular, this space has a map to, I claim to be proved, of course, I'm not doing it here, that this is a modular space of G constellations on C3, of stable G constellation on C3. And there's a natural map on C3 mod G, which simply sends a G constellation to its support, which is actually an orbit of G, is a G invariant, is actually an orbit of G. And therefore, you have a map, C3 mod G is the space of orbits, and therefore you have a map from M theta to C3 mod G. Okay, and for this, we might hope that M theta is a resolution singularities of C3 mod G. And concerning what happens when we go to 0 parameter, stability parameter, there's a funny phenomenon here. If the fixed locus of the G action on C3 is compact, which means there's just the origin, then M0 is what you expect to be the singular quotient C3 mod G. Otherwise, if the fixed locus is not compact, and this is exactly what happens in our case, because the Z axis in this example is fixed, is a fixed locus, then M0 is reducible. It may have many reducible components, and one of them is the quotient C3 mod G. There may be many more reducible components containing stuff that you really don't understand what it is, at least in this example. And also, we have, I guess I'm supposed to talk 1 hour, right?
Yes, 1 hour.
Okay, of course I'm running out of time, but this is the best tradition. So there are also tautological bundles on this quotient, because you simply take the trivial bundle, you make it into a G equivariant bundle by tensoring you attain it by tensoring the structural sheaf by the regular representation. So you get a G equivariant bundle, which therefore descends to a bundle on M theta. And when you decompose the regular representation into its irreducible pieces, you get a number of vector bundles that are called the tautological bundles. And this slide, I think, is quite interesting, because actually what these constellations relate to the equivariant Hilbert scheme of C3, and very often they coincide with it. And therefore, a first result in this, the first results are from the very early 2000s, 2000, 2001. So for instance, Nakamura showed that this G Hilbert scheme is a Krepan resolution of a C3 mod G when G is abelian. And then it's a famous paper by Brigel, King, and Reid, which is called something like McKay implies McKay, where they use for a McKay transform. They showed that the bounded derived category of the equivariant Hilbert scheme of C3 is equivalent to the G equivariant bounded category of C3. And this relates and produces the fact that what Nakamura proved for G abelian is true in general for any finite subgroup of a cell 3C. And then, as I was saying, I believe that the mismatch in the years is due to the publication time of the papers. Ito and Nakajima in 2000 showed that for some chambers, which still we have to define, for theta in some chambers of the stability parameter space, actually M theta is the G-Hilbert schema. So the constellations reduce to G equivariant 0 cycles. And now for G abelian, Craw-Ishi in 2004, if I remember, yeah, I think it's correct, yeah, 2004, proved that these constellations, when theta is generic, are always a Crepin resolution singularities of the quotient, of the singular quotient. And perhaps here I will be brief. You can put up a Kähler description of all this, where instead of the the fine variety that you cut from some vector space or a fine space n is due by some level set of a moment map. And then you know that if the parameter zeta is non-zero, it's sufficiently generic, what you get is a smooth quotient. And in this setting, and this actually means that this space, so this fine variety, is the total space of a principal bundle, because now the action of the compact form of our group is free. Okay, so you have a principal fiber bundle and you get a variety M theta. Note that the font of M is different. Okay, it's not script, because this in principle might be different. And since this is a principal bundle, in a natural way, you can construct the tautological bundles as associated bundles. And here you can prove that the bundles generate the K-theory group, the Grothendieck group of this quotient, and also that the Chern character are a basis of the cohomology ring of M theta. And actually what happens, however, is that when theta is generic, the two spaces, what you get from GIT construction and from the Kähler quotient construction, are isomorphic, or better said, the underlying analytical space of this modular space of a constellation is this quotient, which was born as a analytic variety. So let me spend, I'm not going to deal with the physics really, but I would just I would like to give you the idea that all this has a physical meaning, or at least has a meaning in the theory, in some theories that are supposed to be physics, let's say. In particular, we have some special class of gauge theories. I don't want to go into it. It's a three-dimensional Chern-Simons gauge theory with the two supersymmetries. And in particular, the way we get our objects via Kähler quotient construction is very well suited to allow comparison with physics. And this is a kind of dictionary. What I want to say is just that everything that we have on the left, and these are notions that we have already used, more or less, has a physical counterpart. So, for instance, the space of the linear data we started from, they correspond to so-called West-Zumino fields in the theory. You have a gauge group, moment map. This is a scalar potential. Even the stability parameters in physics are regarded as fields. They are called Fayet-Iliopoulos parameters. The quadratic constraints actually are given by a cubic potential, and this is a meaning in physics. And as usual, our modular space, which is a minimal Crepin resolution of C3 mod gamma, in physics becomes the manifold of the classical vacuum of the theory, as it happens in gauge theory. And the wall crossing, which is a transition from two different manifolds of classical vacua, is what in physics is called a phase transition. Okay, so we have a full, complete dictionary. And then let me just spend the last 7 minutes, or more or less, to talk about the chamber structure. So of the space of stability parameters. So we have, again, this is the definition. This big theta is the space of stability conditions. And then there's, you can prove, it was proved by Craw-Ishi in the paper, that if you take what we call the generic stability parameters, this subset is open and dense, and it's the disjoint union of finitely many open convex polyhedral cones. And therefore, the complement of this inclusion is formed by the faces of the cones, and these are called the walls. So these cones are called chambers, and the faces are called the wall. In particular, the faces to be more precise, the faces of dimension 1 are called walls, and the faces of dimension 1 are called edges. Okay, so we have the usual thing, and what happens is that you can prove that if you move the stability parameter, for instance, in the interior of a chamber, the modular space doesn't change the usual behavior. And also, if you take the relative interior of a wall, so for a generic point of the wall, so to say, the modular space doesn't change. So it makes sense to introduce this relation. You fix, for instance, a chamber, and you consider the modular space MC, or you fix a wall, and you have the modular space MW. And when W is a wall of C, there's a contraction morphism between the two modular spaces. And actually now there is a classification, and you call the wall of type 0 if the contraction actually is an isomorphism. Of type 1, if it contracts curves to points, which more or less means that when you go through a wall, you have flops and flips. And type 3, if the contraction morphism gamma W contracts divisors to curves. This is what will happen in our case. And actually, you could think of about the existence of walls of type 2, where you contract a divisor to a point, but in this problem, they don't exist. Okay, there is no contraction which sends a divisor to a point. And what is interesting is that even when you have a wall of type 0, so when you cross the wall, the modular space doesn't change, the vector bundles may change. The tautological vector bundles may change. So it's a kind of change of basis either in the Grothendieck group or in the cohomology ring that you get when you cross a wall, even in the case the wall is of type 0. And for instance, this is the chamber structure of our example. Of course, it's very hard now to understand anything. And actually what happens is that there are 8 chambers. And for instance, this thing which is more or less green is this cone, and the point here is the vertex of the cone. So this is the farthest point from you. And then the cone opens towards it. Okay, so you have such cones. And here we try to give an idea, drawing just 4 cones. You have this cone structure. And I'm not going to tell you in detail how we'll solve the problem. We solve the problem, the problem I mean of determining determining the chamber structure, in particular to compute the walls, using the Kähler construction, because I forgot to mention that, but actually when you compare the, what is it? When you compare the GIT construction with the Kähler quotient construction, there's a relation between the stability parameter and the level value Z, stability parameter theta, and the level value of the moment map zeta. They are basically the same. So this formula is a little complicated, but in practice, you may think they coincide. They are exactly the same thing. So also using the Kähler quotient construction, you can determine the chamber structure, you can compute the walls, and this is what we did, just computing the tautological bundles and all of that using Mathematica. Okay, so we did it using Mathematica. And we found the following results, just to give you an idea of what's going on. Actually, in our case, which is a C3 mod Z4, we know there's just one resolution singularities. So that means that according to Craw-Ishi's theorem, in all chambers, you find the same resolution of singularities. So any generic stability parameter corresponds to the unique full resolution of singularities. And this also is consistent with the following fact. All walls are of type 0, so nothing happens. But there's one wall which is of type 3. This shrinks the divisor to curves. And then it cannot but happen that when you go through such a wall and you re-emerge on the other side, you get the same variety, because the resolution, the blow up of a divisor is unique. There is no space for doing it in a different way. While in the case of flops, of course, you can contract a curve and then you can explode another curve. No? It's a standard phenomenon. But with divisors, this is not possible. And therefore, everything is consistent. Everywhere we find just the same variety for generic value of the stability parameter, and there are no walls of type 1. On the wall of type 3, we find what is the partial resolution singularities, that we call the y3. Sorry, y3. We find y3. Which just has a one reduced compact divisor. And indeed, what happened is that the non-compact divisor P1 times C has shrunk to the z-axis. And on the walls of type 0, you always find y, and it may be interesting that this is perhaps an interesting phenomenon. On one edge, so it's not, we are not talking about the generic points of a wall. We find a variety which is not a resolution even partial of singularities, because we get a variety which is C times the resolution of singularities of the A1 singularity in 2 dimensions. So it's the ALE space of type A1. Okay? And the projection to our variety is 2 to 1. So it's not birational to C3 mod Z4. The projection is as degree 2. So I think this doesn't contradict anything, because we're not in a generic point of a wall. And I guess it's more or less time to finish. And let me just mention one interesting thing and 2 lines of research we are following now. The first is that, as I mentioned, briefly, our modular spaces of G constellations are fine modular spaces. So on the product of one of them times C3, there is a universal constellation, which is a sheaf. So you may use it to define a Fourier-McKay transform. And then you can prove that the change that you have, the transformation that you have in tautological bundles when you cross a wall, so you have two adjacent chambers on the two sides of the wall, this change is described by a composition of Fourier-McKay transforms. The one from, corresponding to the constellation on one side, and the one corresponding to the constellation on the other side. So it's one of these Fourier-McKay transforms times the inverse of the other. And these describe exactly how the tautological bundles change. I think this is very interesting. And then two lines in which we are progressing. First, it would be very nice to get results. The Craw-Ishi paper is for the abelian case. So it would be nice to understand what's going on in the non-abelian case, how far we can generalize this stuff. And another line of research, which is more differential geometric, is the search for Ricci flat metrics on these resolution singularities. This, by the way, of course, the Calabi-Yau's theorem about the existence of Ricci flat metrics works in the compact case. Here we are in a compact case. Anyway, you can look for Ricci flat metrics. And there is a classical example due to Calabi. Calabi considered the total space of the canonical bundle of P3 as a local Calabi-Yau. And constructed the Ricci flat metric, simply reducing the determination of a Ricci flat metric, I mean the Ricci flat condition, to an ordinary differential equation and solving it, and therefore writing Ricci flat metrics, depending, actually they are parameterized by the second cohomology group with the coefficients in R. This relates exactly one of our cases because the total space of the canonical bundle of P3 happens to be the case of C3 mod Z3, where Z3 acts by cubic roots of unity. Okay. So by matrices that are the product of the identity matrix in 3 dimensions with a cubic root of units. And so this is a classical example, and we are trying to do this, for instance, in our case, and then to find some general theorem. This actually relates with the Sazakian geometry, because, for instance, in the case of C3 mod Z3, this happens to be the space, the total space of the canonical bundle happens to be a Riemannian cone on a Sazakian variety. And also this is true for C3 mod Z4. However, in this case, it's a Sazakian orbifold. So it's a little more general. So I think I will stop here. Thank you very much.
Thank you, Ugo. Are there any questions? Please open your microphone and.
I have a question. So thank you, Ugo, for the very nice talk. Can you put again the slide 29?
Oh, sure. Here. Can you see it?
I see. Yes, I see. So this. So when you have this this wall and chamber decomposition, does this correspond exactly to the composition of the effective cone? Normally we call it the Mohr chamber decomposition of the effective cone. Is this?
I think so.
Okay,
I didn't details of this.
So yeah. So the question would be when you take the union of all these chambers, this would give the effective cone of the whole effective cone of one of the MC or of something in the generic chamber.
So for instance, in my guiding example, I mean the union of all cones is I mean, including the walls, is a vector space. Is the space of all stability conditions, and this is a vector space. In our case, it's R3.
Okay.
So I would expect.
Okay. So.
Please talk.
No, sorry, because I think what I'm not sure if this is the case, but in some cases that I've seen that are similar, this vector space could be seen as a section of the Néron-Sévère space, a section, and then the Morey chamber decomposition of the effective cone would project precisely to this chamber decompositions of the stability condition. I don't know if this is the case in this example.
Okay, yeah, yeah, okay. Thank you very much. It's a very nice thing to check. I would expect that, but I cannot swear. So let me say that it's a good suggestion, and I'd like to understand it. Thanks.
And when you say something in the walls, so there you have a moduli space of semi-stable, right? Semi-stable G constellations.
They may be. What really happens, you don't know.
Okay.
You don't know. Okay. You might have purely semi-stable constellations because you are away from the locus where the stability parameters are generic. So you might have semi-stable. From some computations that I did, in general, not exactly in this case, I know that you can even find generic, you can find stable constellations also on the walls. This is what happens in this case on the walls of type 0. Because nothing happens when you cross a wall of type 0, including on the wall.
Okay. Okay, thank you.
More questions or comments?
I'll ask a question.
Please go ahead.
Try to get the microphone to work. So in the classical McKay correspondence, that's a two-dimensional representation of the finite group, and there are McKay corresponding to affine Dinkin diagrams. So in terms of the on the page 29, the wall crossing all those walls, what's the good way to interpret these walls from this affine Dinkin diagrams in those special cases?
In 2 dimensions, all walls, all chambers always give the same result, right?
Are they just the affine root system, the root system corresponding to walls and chambers? Am I correct?
I don't think it's the chamber structure I'm talking about, because in this case the singularity would be fixed, and then you look for resolution singularities that in principle might depend on a stability parameter, and you find that for all generic values you get the same resolution. Okay, because in that case they are always divisorial, the resolutions. And so I think that the Dinkin diagram is fixed. Is the Dinkin diagram of the singularity you are resolving. So probably we are talking of different chambers.
Oh, I see. Okay, I was curious. And my second question is that, as I mentioned, that in a two-dimensional case, that with a very nice correspondence corresponding to this affine, the algebras affine root systems for type of simplistic cases. So here I saw that you have many different interpretations of in a 3-dimensional case. So, and do you know that anybody who thought what is the kind of object corresponding to in the place of affine the algebras?
Yeah, exactly. So in 2 dimensions, what you have is that the Dinkin diagram, for instance, gives you the intersection pattern of the components of the exceptional divisor. right? It's in particular the intersection matrix is given by minus the inverse of the Cartan matrix or something like that. It's basically the Cartan matrix. In 3 dimensions, it's much more complicated. I don't believe it's completely understood. And definitely, instead of the Dinkin diagrams, you have quivers. And these quivers give you when you have the tautological bundles, you can compute a lot of intersection numbers using the chair classes. You can compute a lot of intersection numbers. These are described by weighted, what is the name? Weighted quiver, yeah, a quiver with the weights on the edges. So yeah, this is more or less written. There's a paper by Reid. It's I think it's a proceeding volume of a conference in Japan. He has a paper there where he describes this stuff, these quivers that generalize this the Dinkin diagram of the 2-dimensional case.
Okay, thank you very much. That's very nice.
More questions, anyone?
Can I ask a quick question?
Go ahead, Rodrigo.
Hi, Ugo. I was just wondering regarding the physical dictionary that you described, like if you know, like you mentioned that these resolutions have an interpretation as moduli space of vacuum on n equals 2 gauge theory. Do you know if they are like the Higgs branch or the Coulomb branch for the theory?
Oof. And this is, I don't know, because I don't know. So this is exactly what happens. Let me circumvent the question in the following way. It's exactly what happens always in gauge theory. It's the branch which corresponds, for instance, when you have, for instance, for instantons, right? You have a supersymmetric Yang-Mills with in 4 dimensions with 2 supersymmetries, okay? And then this relates to a modular space of instantons. S is exactly the manifold of classical vacua. It's this kind of I think this is the Higgs branch, right? But I'm not sure. I never remember too well this stuff.
I'm not sure. I know that the Coulomb branch has this interpretation of like there's some construction like this Guyotto-Mornitsky thing that you compactify a higher dimensional theory or like this super conformal deep theory in 6 dimensions on a Riemann surface, and your Coulomb branch is like a modular space of Higgs bundles on it. So I was wondering if that was related. If this was the Coulomb branch, then maybe it has an interpretation of a modular space of Higgs bundles. But I don't know about the Higgs branch. Like if it's a Higgs branch, then I have no idea.
Let's say that I don't know. I know that this is what I told you. So you have a gauge theory which starts with the classical Lagrangian, and then you decorate it right with the fermions and the supersymmetric partners, whatever. But you start from a classical Lagrangian, and therefore for the classical field theory that you have out of that Lagrangian, you have from a physical viewpoint, you have a manifold of vacua of minima of the action, and that is the modular space that you get. And this is exactly the same sort here. And I don't know more than that, however.
Thanks.
More questions? So I have a question myself, Ugo. So you mentioned at some point that part of the story also leads to some ADHM construction. You had that commutator of A that resembles the Kronheimer-Nakajima construction.
Yeah, it was a comparison, analogy.
Okay. But
yeah.
do you know how to compare this ADHM type or quiver representation with the usual Nakajima quiver or Kronheimer-Nakajima construction? Is there a situation, I don't know, the action of G factors through C2 in which...
I never understood that well, because the quivers that you get are not of the Nakajima type. So, you know, the quiver on Nakajima type is something that by doubling, right? You start from a quiver, you frame it, you double it, and then you get a Nakajima quiver. They are not of this. But I never studied, they may be quite complicated. I never studied their representation varieties, but it might be interesting to see. They are funny quivers. So, but I never did that. Could be another direction of research. No, what I was saying is simply that, of course, you know, here, this seems to be an ADHM constraint, no?
Yes.
Equal to 0. I mean, this is a triple of matrices actually, right? So it's very similar to, and when you have the differential geometric construction, you do exactly that. You know, you have a Kähler form, which is the usual one, so to say. You have a moment map, which is the usual one. You take, you know, and you do the usual thing, and so it's exactly the same construction like in the Kronheimer case for the ADHM construction is the same thing. However, while in the case of the ADHM, the standard one, of course, it's very easy to write down a quiver, right? You have a very easy recipe to write a quiver, and when you build the representation variety, the modular space, I mean, of representations, you relate it to the instant modular space in a clear way. Here, I don't know.
Okay, thank you. Any more questions? Anyone? Okay, so let's please thank Ugo again.
Thank you very much. It's been very nice.
Great, Ugo. Thank